Hello, we are discussing about the video solutions for GATE 1991 paper, and the topic we are discussing is electronic devices. This is the first question came in GATE 1991. A silicon sample is uniformly doped with 10 power 16 phosphorus atoms per centimeter cube and 2 into 10 power 16 boron atoms per centimeter cube. If all the dopants are fully ionized, the material is A. N-type with carrier concentration of 10 power 16, B. P-type with carrier concentration of 10 power 16, C. P-type with carrier concentration of 2 into 10 power 16, D. N-type with carrier concentration of 2 into 10 power 16. The right answer for this question is B. P-type with carrier concentration of 10 power 16 per centimeter cube. So whenever a silicon sample, that is intrinsic semiconductor, if it is added with both pentavalent and trivalent impurities and all the dopants are being fully ionized, then the material is depending on the concentration of atoms. We will see the details now. Classification of semiconductors. Semiconductors is divided into two types. One is intrinsic, the other is extrinsic. Intrinsic is also called as pure semiconductor. We can go for the examples as silicon crystal, germanium crystal. These are going to be the best examples for pure semiconductors. If you are going with silicon crystal, that will be consisting of only silicon atoms. No other atoms will be present. That is nothing but in its purest form. So that is called as intrinsic semiconductor. Whereas extrinsic semiconductor is nothing but pure semiconductor plus impurity. So you are adding impurity to an intrinsic semiconductor, that will be converted into extrinsic semiconductor. So you must have some impurity. So the addition of impurity to the intrinsic semiconductor is called as doping. Doping is the process of adding impurity to pure semiconductor. The type of impurity what you add is giving rise to category of extrinsic semiconductors. One is N-type, the other is P-type. So N-type semiconductor can be formed by adding pentavalent impurity to the intrinsic semiconductor. When you add pentavalent impurity to the intrinsic semiconductor, at that time it will be turning towards N-type semiconductor. Pentavalent impurity, as the name says, it consisting of 5 valence electrons. Out of that one, 4 valence electrons are used for sharing electrons to get stable configuration, like in covalent bond. And the one extra electron will become free electron at higher temperatures. So that will be contributing for the current. If you observe, one pentavalent atom is going to be giving one free electron. If you add 10 pentavalent atoms, that will be giving 10 free electrons. So the number of free electrons available in N-type semiconductor, that is nothing but majority carriers, electrons present in N-type, is equal to how many number of pentavalent impurities you are adding to the intrinsic semiconductor. So that is indicated with Nd. Nd is nothing but donor concentration. The number of pentavalent atoms you are adding to get N-type semiconductor is called as Nd. Nd is approximately equal to Nn. That is, Nd itself is going to be most of the times treated as majority carriers. Examples of pentavalent impurities: phosphorus, arsenic, antimony. Once you have calculated majority carriers, that is nothing but Nn is approximately as Nd, then you can calculate minority carriers using mass action law. This is the equation. Mass action law states that under thermal equilibrium, the product of free electron concentration and hole concentration in a semiconductor is always constant and is equal to square of intrinsic carrier concentration. So from this one you can calculate minority carriers. Similarly, P-type semiconductor can be formed by adding trivalent impurity to the intrinsic semiconductor. Trivalent impurity will have 3 valence electrons in its outermost orbit. It requires one more electron to get the stable configuration. So it accepts one electron from the semiconductor, and that's why at higher temperatures there will be a vacancy created in the valence band that will be treated as hole. Every travelent impurity can accept one electron that will create one vacancy in valence band. So that vacancy in valence band is called as hole. The number of holes for the p-type semiconductor is exactly equivalent to number of travelent impurities you have added. So trivalent impurity is also called as acceptors as it accepts the electron to get stable configuration. Number of trivalent impurities you are adding to form p-type semiconductor is indicated with Na, that is acceptor concentration. How many number of acceptors you have added for unit volume. Examples of trivalent impurities: aluminum, gallium, indium, boron. And majority carriers in p-type are holes. They are approximately equal to acceptor concentration, so pp is approximately equal to Na. Then you can calculate minority carriers using mass action law, this equation. So what we have concluded is nothing but number of free electrons generated in n-type is nothing but number of donors added. Number of holes generated in the valence band is nothing but number of trivalent impurities added. So we can say that one in our question 10 power 16 phosphorus atoms are adding to the semiconductor. Phosphorus is pentavalent so that it can contribute free electrons. So this will contribute 10 power 16 free electrons, and boron will contribute 1 hole, so that 2 into 10 power 16 boron atoms will contribute 2 into 10 power 16 holes. Now the silicon semiconductor is consisting of silicon plus 10 power 16 free electrons plus 2 into 10 power 16 holes. This can be written in this way: silicon plus 10 power 16 free electrons, 2 into 10 power 16 holes can be written as 10 power 16 holes plus 10 power 16 holes. So if you observe that green line, this is the green line. If you observe this one, silicon plus 10 power 16 free electrons plus 10 power 16 holes. Silicon itself is intrinsic semiconductor where the number of free electrons is equal to number of holes. If you add equal amount of free electrons and holes at that time, that also treated as intrinsic with higher concentration, it doesn't matter. So silicon plus 10 power 16 free electrons plus 10 power 16 holes will be treated as intrinsic semiconductor only. So now the remaining is nothing but intrinsic semiconductor plus 10 power 16 holes. The effective number you are adding as doping is nothing but 10 power 16 holes. So the resultant semiconductor is p-type with carrier concentration of 10 power 16 holes per centimeter cube. So we can conclude one important point. When a semiconductor doped with donors and acceptors, the resultant type of semiconductor depends on effective concentration. Effective concentration can be calculated using Na minus Nd with modulus sign. We don't know whichever is larger. And the resultant semiconductor is maybe p-type or n-type. It will become n-type if Nd is larger than Na, otherwise it will be p-type. So this is the conclusion. Correct answer is p-type semiconductor with carrier concentration of 10 power 16 per centimeter cube. Thank you.